Speed of sound lab design. You are in the physics lab with a hollow tube that is open at both ends. You are also given an adjustable speaker that can produce a single tone at a time. The frequency produced is displayed on the speaker. You are told to use the tube to find the speed of sound in the room. A. Describe how you would perform your experiment, including any measurements you would make, and how you would use them to calculate the speed of sound. B. Using the quantities listed in Part A, how would you use a graph to find the speed of sound? A student doing a different experiment determines the frequency and wavelength of sound emitted from a speaker. Graph the data below and use the graph to find the speed of sound. Ensure the graph is properly labeled with correct units and a correct scale so the data points fill up most of the graph. Calculate the percent error given that the speed of sound is 340 meters per second. Describe how you perform the experiment. So, number 1, set the speaker pointing into either of the open ends of the tube. Measure the length of the tube using a meter stick. 2, increase the frequency from 0 of the speaker until you hear a loud sound that then decreases after the frequency is increased a little more. This point of maximum loudness is the first harmonic, or the fundamental frequency, n equals 1. Step 3. Record the frequency displayed on the speaker. Repeat until you find at least 3 more pairs of data, n, f. The first frequency is n equals 1, the next one is n equals 2, then n equals 3, and then the higher order harmonics. Calculate lambda is 2L over n, where n equals 1 again is the first harmonic, and then n equals 2, 3 for the subsequent harmonics. The frequency read off the speaker and the calculated wavelength will be used in a graph to find the velocity of sound based on the equation frequency is v sound over lambda. The speed of a sound wave is expressed by this equation. Lambda is velocity over frequency. Rewrite it as v sound times 1 over f. That equation is now in the form y is equal to mx plus b, the equation for a straight line. Create a graph with lambda on the y-axis and 1 over f on the x-axis using the data from Part A. Plot the points and draw a line of best fit. The slope of the best fit line is equal to the velocity of sound. Here's our data. And then we will complete this third column, which is 1 over frequency. Because of our equation lambda is v sound times 1 over f, lambda will represent y, 1 over f is represented by x, then the velocity of sound will be the slope of our line. So we complete the third column, so you just do 1 over frequency, and we get over there. The next step is to plot lambda, the wavelength, versus 1 over the frequency. After plotting the points, and here they are, 5 points, draw a best fit line. Then pick 2 points that are at the intersection of the graph lines. They will be used to find the slope of the line. These are the 2 points. Now, do not use the plotted data points unless they happen to lie exactly on the best fit line. The best fit line replaces the data points and helps to smooth out experimental uncertainties. Use the 2 picked points and find the slope of the line, which will be the calculated speed of sound. Then find the percent error. So here, v sound is the slope of our line, which is delta lambda over delta 1 over frequency. Substitute in our values for delta lambda, and here's delta 1 over f, and we get 348 meters per second. The percent error will be the absolute value of 348 minus 340, which is the measured or the generally accepted speed of sound, divided by 340 times 100, and we get a percent error of 2.4%.